which is basically let's say a different result, which considering the ones we have already published. So as a matter of motivating the study of neutrinos, I'd like to present this quote by Dave Schmidt, saying that in order to understand the universe that we live in, it looks like we need to understand the neutrino. So it's kind of an important statement in motivating also the realization of some experiments, considering that neutrinos are taking or having some effects not only on the realm of particle physics, but also on cosmology and astrophysics. In addition, well, there are many things already we know about the physics of neutrinos. For instance, we know that neutrinos are the most abundant massive particles in the universe. And because of that, and because of the very tiny mass they have, they contribute somehow and a little bit on the composition, the content of the dark matter. And because they interact very weakly, but also have some small gravitational interaction, then they will have some effect on the structure and formation of the universe. And one of the very nice thing is that we have many sources of neutrinos, which we can use to study them, including those that we produce. I mean, the sources we can build here at the very same Earth. So in addition, there are some other things we don't know. And for instance, there is the three first questions written here, if whether there is maximal mixing, if CP is violated, and how many neutrinos there are in the universe, in the sense, and how many types of neutrinos there are. Those questions are possible to be studied through neutrino oscillations. But there are more questions. For instance, which is the heaviest and the lightest neutrino, because so far we haven't been able to determine that, and what is precisely the mass of the neutrinos, and also the so-called nature of neutrinos, whether they are neutrinos and neutrinos are different or the same particles. These three last questions are not possible to be defined or studied through neutrino oscillations, or are not being considered at all during this talk. So after this brief motivation to study in general the physics of neutrinos, I would like to talk a little bit of very brief introduction or review, better to say, about neutrino oscillations, and then I will include the non-standard interaction precisely. Then I will present some introduction on details about the NOvA experiment to go to the analysis of the data and the results we have obtained between these analyses with neutrino oscillations, and finally some conclusions. So to discuss about neutrino oscillation, the first thing one would need to understand is what we understand about the flavor of a neutrino. So we define somehow that neutrino flavor alpha is created in a W boson decay, and it is produced together with a charged lepton with lepton flavor alpha. Sorry. So this is what we understand by a neutrino with a specific flavor. In principle, this neutrino can propagate in space-time and then at some point be detected or observed, but we actually do not see the neutrino, but produce it lepton with the same flavor, a charged lepton with the same flavor. Then in that point, we can in principle say that there is a neutrino with a specific flavor alpha in this case. However, it had been observed that this flavor may change. That means that during the propagation, there is something happening that that makes that the neutrino at the point of detection would change its flavor. Then we will observe a lepton, a charged lepton with a different flavor compared with the one we started with. And this is only possible if neutrinos have mass and actually they mix. And these characteristics of the mixing of neutrinos is usually parameterized in this way. We consider the situation where there are three specific neutrinos with a different type. In this case, we call them the flavor neutrinos, electron and muon and tau. And these are precisely the neutrinos that we can detect in well, first we can produce and detect. These are the so-called interaction and eigenstates. And then there are The mixing is parameterized with this mixing, so-called mixing matrix, and they are then what we say that the interaction against states are a combination, a linear combination of these three massive neutrinos, nu1, nu2, and nu3. Those are the mass eigenstates. They have definite mass, and they are actually the states which propagate through space-time. And now this mixing matrix usually is parameterized in this way. This is the most common parameterization and the one we use to use in the analysis of the study of neutrino oscillations, where basically the mixing matrix then is a product of rotation matrix. One of them, the middle one, including a CP violation phase, each one written here specifically. So you can see that basically what we are doing is rotating one vector space, the mass states, flavor states. We are rotating them into a different vector space, which is with the one with definite flavor. In general, we can study these three mixing angles and the delta CP, which are then 4 parameters already included in the oscillation phenomena. We can study these parameters through 3 different kind of experiments. So these are the so-called the atmospheric or accelerator neutrinos, the solar neutrinos, and reactor neutrinos experiments. So each of these 3 kind of experiments can prove the corresponding mixing angle as depicted here. So what I'm going to present in a little bit are precisely a discussion about the accelerator mixing parameters, yeah, because well, NOvA is actually not an accelerator neutrino, but then through solar experiment, which actually is very one of the more known experiments, because it was one of the experiments which actually concluded definitely that were oscillation. Then we can prove this sector with the R12, the so-called theta12, parameter. And through the reactor experiment, we were able to definitely measure theta13. And maybe some of you know that until around 2012, we used to say that theta13 was very, very small, and usually we neglected it in order to analyze in a simple way all these processes of neutrino oscillation. Now, this mixing matrix and the fact that neutrinos are mixed leads finally to the possibility to study how probable it is to detect a neutrino with a specific flavor different to the flavor which it was produced initially. And this amplitude, this probability is basically a computation made by the quantum mechanical techniques. It's kind of easy to demonstrate that the probability that a neutrino of flavor alpha, after traveling some distance during some time, is detected with a flavor beta is given by this expression here, where we have in the U element matrices, the element matrices of the mixing matrix, sorry, and then the appearance of the neutrino masses, specifically the square of the neutrino masses. Notice then that in principle, if there is no masses, or if all neutrinos were massless particles, this probability would be null. I mean, the neutrino will preserve its flavor. Now, you can also notice that to compute this quantity, one needs still to compute the square of this expression here. That makes possible that actually the oscillation probability would depend not directly on the masses of the neutrinos, but on the difference of the square of the masses of the neutrinos. It also depends on the distance, I didn't say it before, but it depends on the distance traveled by the neutrinos and the energy of these neutrinos. So this is basically the general expression what would use to study the neutrino oscillations, and in principle in the 3 neutrino mixing. So we are considering specifically 3 flavor neutrinos and in a minimal number of 3 massive neutrinos. These parameters which appear here are precisely the matrix element are basically dependent on the mixing angles I presented before here. So through the different experiments we have measured already with some precision these parameters, and I present here just an initial like an initial taste of the values of these parameters. So you can see that, for instance, theta 1,3 is in fact a small one. It's not zero in any case, but it's a small angle. This parameter here, 49.2 degrees, is something that appears in many of the global analysis of all the data that had been obtained from oscillation experiment, the different kind of oscillation experiment, but there is a very large uncertainty on this parameter. Theta 1,2, on the other hand, has been very well measured. So one of the questions we are willing to answer through neutrino oscillation experiment is, for instance, if this parameter is correct or we have a different value. There is a possibility that the mixing angle theta 2,3 is closer to 45 degrees, which would mean that there is a kind of symmetry between the mixing of muon neutrinos and tau neutrinos, and it would imply some interesting physics that we will have to understand. On the other hand, through this experiment, we have measured two different values of the delta m squares here in the oscillation probability, and you can see these two are very apart from each other. One is smaller than the other, but there is also a question here, a remaining question to answer, which is the sign of this parameter. So we don't know exactly if you see delta m squared. I'm sorry, I didn't define that. Delta m squared means the difference between the square of the mass k minus the square of the mass j. So in this case, what happened is that we don't know, we are not sure whether the neutrino number 3 has a larger mass than the neutrino number 1. If this number is positive, then it means the third neutrino is the one to have the largest mass, and the order would be 1, 2, 3, like, and we call that an order, normal order. So 1, 2, 3 is the normal order. But it could happen that the neutrino, which we label as neutrino 1, could be the one with the larger masses. Then that would mean that the M3 would be the lightest neutrino, the nu3 will be the lightest neutrino. So we will have the order given by nu3, nu2, sorry, nu3, nu1, nu2, and this is what we call the inverted order, just because of that, because it's not 1, 2, 3, so we change the order. So this is another question we have. We have to understand what is the case in the neutrino phenomenology. So what I said before is that, in fact, we have like a plethora of experiments that have measured this parameter here with precision. And I put it here to stress that there are these 4 different kinds of experiments with an example, with the name of the example of each sector. The channel we have studied, for example, in the solar neutrinos, or in the solar experiment better, we have studied the disappearance of electron neutrinos, because the sun produces mainly has a flux of electron neutrinos, so we can study whether there is a neutrino muon and neutrino tau appearing. On the other hand, the reactive neutrinos produce basically a flux of antineutrinos, electron and neutrinos, so we can study the oscillation to these other flavors. These are the names of the example of experiments that have been running or are running, some of them. And on the other hand, we have the atmospheric accelerators, where in general we can study muon neutrinos or muon antineutrinos to see whether these neutrinos oscillate into a tau neutrinos or electron neutrinos. And the idea to present this slide here is to make clear that these two sectors kind of separate each other, and that is the reason why some years ago it was enough to study these sectors independently, like if there were only 2 neutrinos, but still we know that because there are 2 different delta m squared, then there must be, this is absolutely necessary, that there should be 3 neutrinos and not only 2. Then from the point where we would understand that the reactor mixing angle is different from 0, then we started to understand that it was necessary to study the oscillation phenomenon in the full way, so included the 3 neutrinos. So this is something I wanted to clarify. All this matter of neutrino oscillation is studied basically through the evolution of the, as I said before, the massive neutrinos. And this is described in a effective Schrödinger equation like this, but having in mind that the massive neutrinos are a linear combination or are mixed into flavor neutrinos. In principle, each massive neutrino will have an energy defined by this expression here, the usual one, and it will imply the oscillation as I explained before. However, we have to consider that neutrinos not always travel in vacuum, but there is sometimes some specific systems, for instance, in the sun or even on the Earth, that neutrinos will have encounter matter. So we have to take into account this possible interaction. Usually it is parameterized through this effective matter potential, which has this form, which is including, it does include an interaction of the kind of charge current and the neutral current. On Earth, it is basically parameterized in this way, where N, E, R, N, N are basically the number, the number density of electrons and neutrons, which neutrinos would encounter through while they are traveling through the matter. In the Earth, basically, we only will find matter which contains electrons and non-muons or taus. So this is the reason why only a number of neutrinos are considered here. When you include the matter potential in the oscillation probability, it has the effect that, well, this is another way to represent the new Hamiltonian, including matter. Here, then only the charge current potential is included because, as you can see here, the neutral current, maybe it's clear that the neutral current will be the same for the 3 different kind of neutrinos, the 3 different flavors. So it basically is written in a matrix form. It would be proportional to the identity matrix in that case. So we can factorize it, and it will not have any contribution to the oscillation probability. And the truth is that considering the matter, the net effect on the oscillation probability is that it became enhanced. So this is the so-called well-known MSW effect. I mean, every oscillation analysis, or better to say, every analysis studying the data coming from the different experiments should include this consideration, even though in some cases the matter effect, so the density, for instance, is constant. It doesn't matter if it is constant or not. You have to consider it to study properly the neutrino propagation in matter. Okay, so now this is also important because it will give us the possibility to differentiate when, first of all, differentiate what is the effect of the CP phase. So the CP phase essentially would imply a different behavior in the neutrino channel with respect to the anti-neutrino channel. So these are so-called by probability plots, where one see in the horizontal axis the neutrino oscillation probability, while in the vertical axis the anti-neutrino oscillation probability. If there is no matter, then the only change on the oscillation probability is given by the CP phase, and you can see here for the 4, let's say, characteristic values of the possible values of the CP, you see that the oscillation probability would move around this ellipse here, depending whether we have neutrinos and antineutrinos. However, when the matter effect is considered, we not only are able to study the changes given by the phases, but also we will be able to study where the masses are ordered in the inverted case, or in the normal way. So this is
these are, excuse me, these are atmospheric neutrinos.
What's that? Can you repeat?
These are atmospheric neutrinos.
wait, okay. They would be atmospheric neutrinos, but actually we are using specifically some parameters. For instance, the length traveled by neutrinos, we are using those given in the NOvA experiment. So not only the length, the distance traveled by neutrinos, but also the characteristic energies of the neutrinos are those we study in NOvA. But the mixing parameters are basically those produced also in atmospheric neutrinos. Mm-hmm.
Okay, thanks.
Okay. So this is why, well, not only because it is the correct way to do it, but also because of this interesting result that we have to study or consider the matter effects between the neutrino oscillations. Now, a part of the question I presented before that we can study through neutrino oscillation, there are beyond star model things that we can also study through this phenomenon. In particular, the one we are interested in this talk is the non-standard interaction. On the right of the slide, you can see a plot where some time ago these authors here presented how neutrinos oscillation, including non-standard interaction, might reproduce better some expected result by the SNO experiment. So in this plot, the black dashed line corresponds to the standard MSW, so standard oscillation only, and the magenta or pink plot corresponds to the case where neutrinos in non-standard interaction are included. So you see that in the so let's say low energy region, both of the situations are basically giving the same prediction, but for the high energy neutrinos, there could be some differences, and there will be actually some difference, and depending on the uncertainty produced in this experiment, then we could give some insight of whether there are or not neutrinos, non-standard interaction. In addition, there have been studies and proposed that in fact there are many implications that can appear in the presence of the non-standard interaction, in the sense that we would need beyond the standard model physics to explain that in those interactions. So for instance, I would like to highlight the idea that there could be some light mediators, so there in principle the possibility to include additional interactions there. Certainly, the dynamics of neutrinos in matter would change considerably, and there would be some impact in the oscillation probability in principle. And of course, that would result in a possible interference with the determination of the standard parameters. In general, one can study two different kinds of neutrinos non-standard interaction, which are charge current or neutron current, but those having a more direct effect on the oscillation are the neutral current non-standard interaction. This is the parameters I am studying in this talk. On the other hand, the charge current interaction would have more directed effect in the process of producing neutrinos or detecting them. So these are, I am not considering that. I am going to focus only on neutron current non-standard interaction. Okay, so the net effect of the inclusion of non-standard interaction is parameterized in an effective way through the addition of a matrix representing or containing all the new parameters which govern the non-standard interaction. Each of these epsilon is parameterized in terms of they are in general complex numbers in general, but I would clarify something a little bit. Then it would include a magnitude and a corresponding phase. Remember that the Hamiltonian in principle is a Mitchell matrix and there is the property of unitarity. So what that implies that diagonal terms of the matrix that must be real quantities, but the off-diagonal ones are in general complex represented, as I mentioned before. In principle, the addition of these new parameters will in particular imply that if we refer to the diagonal terms, then even in neutrinos were massless, there could be the effect, this new parameter will have the effect of different effective mass square difference. On the other hand, the off-diagonals include the possible role of mixing angles, as the mixing angles I defined before, And also because of the inclusion of this phase, then there could be a new source of CP violation, so implying or giving an additional relevance and interest on these new parameters and the non-standard interaction. Okay, as a matter of percent how, in fact, the oscillation probability changes through the inclusion of these new parameters, I present here precisely the so-called disappearing channel, so a muon neutrino. I'm trying to present here the survival probability, so how it's possible to that the neutrino do not change its flavor. And you can see here that setting the phase, the new CP phase to 0, by changing only the magnitude, we can see that the one that has a larger effect is the epsilon mu tau, for instance. I am using here the standard oscillation parameters that the NOvA experiment has measured so far, or has used so far. So this is for the disappearance channel. This is for the appearing channel, where a muon neutrino will oscillate into an electron neutrino. In the case, you can see again that the two that have the largest effect at epsilon e tau and epsilon e mu. You can also see that I didn't consider the diagonal term, basically because we understand that NOvA is not sensitive to those parameters, so we only focus on the off diagonal terms. Also, for these two plots in particular, the phases are set to 0. The new CP phases are set to 0. This is for neutrinos, and here this is for neutrinos, and here I present you the effect of changing the phase. So I selected here a rather large value for epsilon e tau in this case, and varied only the corresponding CP phase. And you can see that the change produced to the oscillation probability is rather large. So we, in principle, would be able to observe such an effect on the NOvA data. This is for the E tau sector, but if you go to the E mu sector also, you can see the very same effect. The oscillation probability is very evidently changed. So it has an important effect on the data we collect. So now let me go to a brief and quick description of the new mean of axis electron neutrino appearance experiment, NOvA. The NOvA experiment is run by the NOvA collaboration, which is a group of around 260 physicists, scientists, and engineering, all of us coming from 8 different countries, around 60 institutions. And this is a picture of how the neutrino would be seen. We have a detector located at Fermilab and another detector located at the northern part of the US in the border with Canada. Basically, NOvA is composed by, well, it's a log baseline neutrino experiment. It's composed basically by 2 detectors, the one we call far detector and near detector, and neutrinos are produced in the so-called new me beam at Fermilab, basically composed of muon neutrinos. I will talk a little bit later on about that. The 2 detectors we have are basically equivalent in the way they function and the way they are built. The great difference is that the size, the near detector is only 0.3 kilotons, while the far detector is 14 kilotons. The near detector is located around 1 kilometer away from the source here at Fermilab, the neutrino source at Fermilab, and it's underground, around 100 meters underground. On the other hand, the far detector is located on the surface, which means that it is not shielded against cosmic rays, which we need to study in such a way that we identify properly each event, and we don't confuse, let's say, neutrinos coming from any reaction in the atmosphere or with neutrinos coming from our beam. The 2 detectors have a particular location with regards to the neutrino beam. It is called off axis. They are not located in the middle of the axis, but moved around 14.6 milliradian. And the reason for doing that is we wanted to make neutrinos almost monoenergetic. And then you can see in this plot here the spectrum showing that if you place the detectors on axis, then you will have a very intense flux of neutrinos, but with a rather wide range of energies. Instead, if we choose the 14.6 milliradians of axis, we can build a neutrino which has a very big flux around 2.2 GeV, and most of the neutrinos have this precise energy. So that's why I say that they are almost monoenergetic. So this is basically the consideration of the setup, experimental setup. The physics vault we have with NOvA is, well, studying the muon neutrino and antineutrino disappearance and electron neutrino and antineutrino disappearance in a beam which is mainly composed by muon neutrinos. Through the study of these processes, we measure these three oscillation parameters. We also are capable to try to determine the mass ordering. And in addition to neutrino oscillation, we can also study neutrino interaction and define and measure some cross sections and study some physics beyond a standard model, like the possibility of the existence of stereo neutrinos. In addition, we have set that experiment so that we are also able to study neutrinos, so neutrinos coming from possible supernova, and some additional exotic physics. We called it more exotic, for instance, monopoles and physics related to gravitational waves, and of course, neutrino non-standard interactions. This is the way the beam is produced. So we have a beam of protons produced at formula. These protons are directed to a target, mainly composed by carbon. This is basically a bar of graphite. In the interaction, the collision of the protons against this target produce a bunch of pions. And these pions, in principle, decay after some time, producing mainly a bunch of neutrinos, a beam of neutrinos. But in the process of protons scattering off the target, not only, we can produce positive and negative pions, which in the decay depicted here in the squares or in the rectangle here in the bottom, produce neutrinos or antineutrinos, muon neutrinos or antineutrinos. So we have set up here a focus horn, which basically consists of magnetic field, which focus only one charge or one kind of pions, giving us a neutrinos or antineutrinos depending on the situation. So when we focus the positive pions here, we produce neutrinos following this chain here, and then the beam is a very pure beam of muon neutrinos with some contamination of antineutrinos and electron neutrinos as shown in these numbers here. When we focus negative pions, then the beam is composed mainly by muon antineutrinos, and you can see here the spectrum, and also the small contamination from muon neutrinos and electron neutrinos in this way. So in this way, we build our beam, which are directed to the detectors, and we count the number of neutrinos in each experiment. The detectors are built in this way here. You can see that there are kind of walls built of like tubes. These are made of PVC, and you can see that there are horizontal tubes and there are vertical tubes as well, that allows us to have a two-dimensional view of the process or the interaction produced by the neutrino. Each of these tube or holes here is filled with a liquid scintillator, and also we include there a optic fiber which collect any radiation produced by a charged particle crossing the liquid scintillator. The light collected by the fiber optic is then transported to this device, which is basically a photodiode, which give us the information about where the interaction has been produced, or where the neutrino, the charged particle has crossed inside the detector. So you see here, basically these colored points correspond to a signal of a light produced by or detected by the photodetector, and implying that there was some charge or some energy deposited in precisely that point. Following the trajectory of these dots, we can reconstruct the track, the track produced by the particle, and then finally reconstruct as well the vertex where the interaction with the neutrino has been produced. Certainly, this characteristic of the detector also can allow us to configure or distinguish between different interactions and then between different neutrinos. We have understood that, for instance, a muon neutrino will create a muon which produces a large track, a considerably large track. So this is like the signature of this kind of experiment. Sorry, the event. While if we have an electron neutrino, we have a shower here, an electromagnetic shower, which is produced basically because of the interaction of an electron traversing the muon scintillator. The liquid scintillator. Then in that case, we will identify this event as a neutrino, electron neutrino charge current event. And there are some other kind of events which are here produced basically because of the decay of a pi zero. And then there is an electromagnetic shower, which is very white and easily identified as a neutral current effect. But in that case, we cannot identify which flavor of neutrino has produced this interaction. So to distinguish this and considering we can have these characteristics, specific characteristics for each event, we have implemented a so-called convolutional neutron network, which basically is a machine learning technique to distinguish specifically when a neutrino has interacted in the detector and when an electron has interacted in the detector. This technique has worked.
You can have also elastic collisions, right?
Sorry, repeat.
Elastic collisions of the neutrino.
Oh, well, actually, the only possibility we have is to detect charged particles. So in principle, we would not find elastic scattering of neutrinos because we are not shooting neutrinos against neutrinos. So in principle, no.
In SNO, they measure the elastic collisions. It's part of the analysis. They have sharp collisions, neutral currents, and elastic collisions also.
Well, I would say that
the neutrino goes in an elastic collision with electrons or whatever.
Yes. So what I was going to say is that as far as the interaction produce the position of energy inside the detector, we can detect it. However, for the neutrino oscillation processes, then the events we are interested in are these ones here, specifically, more importantly, the first two, because these are the events that allow us to identify whether we have a muon or electron neutrinos. That's it. That's the thing here. Thank you to your question. In principle, I would say that is possible, but we don't pay attention to those kind of processes. Okay, so let me go a little faster because I don't have much time, I guess. So this is we have developed very, let's say, precise techniques to identify the events and then to identify when we have an electron neutrino or a muon neutrino. And this is important because this is the way we count, let's say, how many neutrinos we have in each detector. And in fact, this is the technique we have been using for the last few years, and the most recent result were recently published and featured in the physics journal. And what you can see here is just an example of what we do, which is present constraints on this pair of mixing parameters, for example, the mixing angle θ23 and delta Cp. And in this case, we see that for the normal ordering, basically we have every value of delta Cp allowed, but while for inverted order, only a region of delta Cp values are allowed. In any case, our results favor normal ordering. And the other thing important to notice here is that we are comparing against the recent result by T2K, which is the other experiment studying this phenomenon in very similar fashion than ours. And you can see that, for instance, in the normal ordering, there is this difference, which is in the community is usually referred as attention. Well, we only say that there is a difference just to maybe inspire you to pay attention to future experiment, for future results. We are working together with the T2K collaboration in order to make a proper combined analysis and define whether we have this tension or not. Of course, what I am presenting you here is basically an extension of this previous analysis, and the important difference is we are including NSI, non-standard interaction. So the other important thing to consider, which makes the analysis a bit different, is the relevance we have to, or the attention we have to pay on the matter density. It's essentially because the signal we will study is proportional to matter density, and the fact that neutrinos travel up to an 11 kilometer underground, interacting with all the matter they will encounter during the travel from Fermi to the far detector in Ash River. We have implemented some techniques to study the density during this trajectory, and we have set an average density of 2.74 grams with an uncertainty, so included in the analysis, an uncertainty of 3.7%, so that it is included in kind of a systematic into the analysis. On the other hand, another important thing to take into account is that as we are not sensitive to all the oscillation parameters, we have to use the information coming from other experiments, for instance, other experiments or people who are working on global analysis. So, for instance, we consider the value reported on PDG, particle data group, or the NewFit, which is the group, one of the group making this global analysis. However, an important thing we have to consider is that in some cases, this combination could include neutrinos traveling through matter. So it means that it is possible that some of the results are affected by a non-standard interaction and they are not being considered. In one study performed in 2011, it was found that, for instance, the solar plus Camden data would prefer NSI, non-standard interaction, at 1.9 sigma. It means that it is still possible that it would be possible that some non-standard interaction have not been considered in this global analysis, so that we are trying to avoid that. To do so, we decided to include these three parameters given only by reactor experiments, mainly Diaby, Reno, Chose, and Camden. So you can see here the difference between the values considered in this analysis and the value reported in the PDG. And in particular, you can pay attention to the θ12 value, which for us could be a more conservative value, or including its uncertainty, and it includes or covers perfectly the PDG value. So basically, the only difference is that matter has no effect on this measurement, because basically all reactor experiments are built such that neutrinos travel very short distance, and basically their interaction with matter is safely neglected. So with all that say, I only have to say in addition that our analysis is performed such that in the NSI matrix, potential matrix, each parameter is considered independently. So I'm going to present constraints on epsilon, for instance, but E mu and E tau only. And in the analysis, all the other parameters are set to 0. Complete analysis is very complex and obscure basically all possible results. So this is a spectra obtained by NOvA. So the points are basically the data obtained in the FAR detector, showing us the number of events. On the left-hand side, you see the electron neutrinos or antineutrinos, and on the right-hand side, on the right, you see the muon neutrinos. Basically, the conclusion is that we don't actually need a non-standard interaction to explain our data. We are comparing here, well, the blue line corresponds to our best fit, including non-standard oscillation, while the red dashed line corresponds to the three flavor analysis and the best fit prediction. You can see that the two lines are basically overimposed, and the colored band corresponds to the 1 sigma uncertainty in the three flavor analysis. So you can see also that our best fit with non-standard interaction is perfectly inside this region. This is the case when epsilon mu E mu is considered, and there is not much of a difference, but this is the result considering only epsilon E tau. So you if I go back and forward, you see a little difference on the blue line, which is the one which should change because the NSI parameter is the different one. Oh, sorry. You see here the difference, but still in those cases, our prediction with non-standard oscillation falls inside the three flavor oscillation, and our analysis only gives an improvement of 0.75 units in the chi-square. So basically, no evidence of non-standard interaction. This can be used to generate this kind of plots, which give us the constraints on the oscillation parameter. On the non-standard oscillation parameters, non-standard interaction parameters. Sorry, and as you can see here, we choose to plot in the horizontal axis the sum of the two phases, the CP standard phase plus the non-standard phase. In this case, you see that the net effect on the possible CP violation is that we cannot measure CP violation, and only that the magnitude of the epsilon E mu should be lower than 0.2, 0.3. A similar result is obtained here for the E tau region, where basically the epsilon E tau should be lower than 0.4, but there is this interesting sector here appearing as a degeneracy. So it appears that there will be an allowed region for the parameters for a rather large value of epsilon E tau and a specific value of the CP violation. However, I can explain this appearance here in the following way. I present here, I'm showing you here the spectra for electron neutrinos for a different combination of parameters. So the black line corresponds to the standard oscillation, 0 NSI, while the two other lines correspond to the changing the epsilon E tau parameter in this way. So you can see, for instance, on the left that for neutrinos, the blue line is basically indistinguishable from the black line. And then there is a degeneracy there. This degeneracy, however, can be broken when we go to anti-neutrinos with the same set of parameters. Then the spectra would change considerably, and these parameters here are around close to this region, which is supposed to be allowed. Now, if we move a little bit from 1.9 to 1.5, you see that the degeneracy in both cases are still present. Is still present. So we cannot distinguish between the standard oscillation and non-standard oscillation. That is the reason why the degeneracy produced this allowed region for large values of epsilon E tau. Another way to show this is if we compare the oscillation probability of muon neutrinos going to electron neutrinos in the presence of NSI with the absence of that, or the standard case for an energy of 1.75, you see that the two curves coincide precisely in this point here, which is precisely this region where the allowed region in the NSI parameter or the phase space is present. So this degeneracy will in principle produce precisely the contour of allowed parameters or allowed values for this NSI parameter in particular. In addition, we can also study a comparison between our results and the minus ones. In our result of 2017, they found these contours where they were not allowed to restrict the parameters on this region here. The rectangle here is pointed to the same region we found here. And what our results that show that all these a large part of this region is excluded completely, but still to notice also that Minos has already observed this degeneracy, and our result kind of break it, but not completely, unfortunately. We can also see the effect on the standard oscillation. These two plots here, these two sets of plots show what happened when we include the epsilon e mu, for instance, or epsilon e tau into the fit. And our conclusion is that basically these regions are not modified considerably. So effectively the disappearance of muon neutrinos basically is not affected in NOvA by the presence of NSI. However, the disappearance of electron neutrinos is very much affected, and this makes our this actually breaks our possibility to measure delta Cp properly. And this is represented in these plots here, where the blue contours represent what the NSI would allow. Instead, in comparison with the with the standard oscillation, with the lines crossing here. So basically, the inclusion of a non-standard oscillation will spoil our measurement of delta Cp. Okay. So this is basically the most important result. And to conclude, definitely we, in principle, our data, to explain our data, we don't need a non-standard interaction. And we are posing a constraint on epsilon e mu and epsilon e tau, but remember, it's important to clarify with that we still have some degeneracy at high values of epsilon e tau specifically, and it is certainly true that including non-standard interaction makes it more difficult to measure delta Cp. So this is what I wanted to present. I appreciate and thank you very much for your attention. And yeah.
Mario, thank you very much for the very nice and complete talk. Question from the audience?
I have a question.
Yep, please.
I didn't understand why the separation in delta Cp plus delta E nu. What
Right.
what does it mean? I didn't understand that. What?
The point is that when you develop the whole oscillation probability, basically the point is that the oscillation probability will depend directly on the sum of these two parameters, on the sum of delta Cp and delta E tau. So it is at least it's difficult for our data and our sensitivity to distinguish between the Cp valuation produced by the standard.
Why is the delta E tau doesn't violate Cp? I mean, what?
See, yeah, exactly. Delta E tau would represent, and the same for, sorry, if I go back, delta mu. Delta mu is a source or a measure of Cp violation, but produced by in principle, non-standard interaction, if they exist.
And delta Cp, how is defined?
Oh, delta Cp is the, oh, well, defined is the standard, sorry. It's in the, sorry, I go back to the first section here. Okay, there. Here, this is a proper property of the
The usual
mixing of.
phase in the CPM matrix.
Yes, exactly. And but this is properly coming from the standard oscillations. Sorry, from the standard interaction. So a standard model, let's say, basically. Yeah.
Okay, thanks.
Okay, thank you.
Physically, how do you measure DCP violation? What's the effect? I mean, what's the physical effect that you're getting that measures CP violation? I'm sorry, but I think it.
Yeah. So essentially, we understand that CP violation will make neutrinos behave differently from antineutrinos. So in the oscillation, this is why this plot is performed, because if neutrinos and antineutrinos are different, so there is CP violation, then the number of events coming from the neutrino sector would be different compared against the antineutrino sector. So if we are able to distinguish between these two cases, we can measure the phase.
Yeah.
In NOvA and some other experiments, we have the possibility to build neutrino beams and antineutrino beams. So in principle, we are able to give some information about that.
Okay, I understand. Okay, thank you.
Okay.
More questions?
I have a question.
Yeah.
Yeah, can you? Oh, sorry. So, can I make a question?
Please continue,
Yeah.
Sebastian.
Okay. Yeah. Can you explain how you estimate the backgrounds? Because I saw in one of your figures that the backgrounds are very small.
How you estimate what? Sorry.
Background.
Oh, okay. Yeah. Well, there are, let's say, some quite many possibilities of background, but essentially, well, for instance, one first source of background could be the contamination of the beam. So when we work with a beam of neutrinos, then there is this contamination here, and but the interaction at the in here, for instance, would be distinguishable. This is one thing, or will be different. I mean, this is one thing. The other thing is, for instance, for possible neutrinos coming from the atmosphere, then there is the directionality. So in principle, what we should observe in this plot, not better in this one, we should observe that is that the neutrinos, the particles produced by a neutrino interaction coming from the beam should move in a preferred direction, and then we determine the angle between the direction of the beam and the track of these particles, the charged particles produced in the detector. Another way to avoid or to count for background is to ensure that the events we are considering and classifying are fully contained, and it means that not all the full volume of the detector is considered, but only a region. So we say, for instance, that when we reconstruct the vertex should be in the center, for instance, at a distance from each side of the detector. That would allow us to avoid to count possible events produced by, for instance, the rocks surrounding the detectors. Well, this is basically the most important backgrounds we are considering.
Yeah, but in one of the figures that you have later,
Okay, you say you mean the spectrum.
Yeah, I
probably.
mean the backgrounds that you cannot reject. Yeah, for example here.
Yes, yes. So when I refer to round sig background is because we mix neutrinos or with antineutrinos. We try to avoid that, and we have some certainty, or better to say uncertainty, that we can do it in a rather good way or not. So we have to include that. The big background is what I said before. Each time we fire neutrinos, there is a possibility to have some antineutrinos, but again, neutrinos and antineutrinos would produce charged particles with a different charge, so we can distinguish them, and then with some precision again. And again, the cosmic background, it's because of the directionality basically, but those, again, we have some precision to distinguish them, so we have to include some possible background cosmic neutrinos which are counted as neutrinos from the beam. So this is represented in the bar here. And then in the analysis, the oscillation of neutrinos or the neutrinos are counted, simulated in such a way that including this background are oscillated and produce specific signals in the far detector, which at the end are represented by these points here. Hopefully,
I see. Yeah.
Okay.
Thank you.
Thanks.
Yeah. A question, please. Hello, can you hear me?
Yes.
Oh, yeah. So my question is about the vertex resolution. Can you tell a few words, please, about where is your vertex resolution and how exactly you determine the position of the vertex of the neutrino?
The position. Okay.
Yeah.
This is
basically also the...
in fact, this is a process which is not in which I am not an expert, to be honest. But the point is precisely to rather simply place it is that in each of the in each of these points, it means that there was some energy deposited by the charged particle traveling to the detector, specifically interacting with the liquid scintillator. Then we have also built some techniques which allow us to collect all these points so that we can construct a possible track. And in principle, also, we not only collect each track, and then you can see that the particle 1, 2, 3, and then not only individual tracks, but we also have to detect, let's say, additional tracks to corresponding to the other particles which are produced. For instance, here there is a proton and a muon. Here there are pions and whatever, and then we have to collect all the information so that we can reconstruct various tracks, a number of tracks, and then all those tracks, in principle, should more or less be focused up to one single point. Another thing I should say that obviously these processes have a lot of uncertainties, and then we can include those uncertainties into the analysis, like systematic effects, which will affect our final result. Now, the precise point of unfortunately, I didn't include here an example of event, but yes, the exact point here is basically reconstruct through the projection of the tracks of each identified particle, and with some uncertainty, we can also then reconstruct not only the position, but also the energy, which is more important for our analysis because the oscillation depends specifically on the probability, on the energy. And the position specifically in the detector will not be, let's say, important because in any case, the size of the far detector is, even if it is large, is rather small compared to the distance traveled by the neutrino, which is of the order of 800 kilometers. I'm not sure if that answered your question.
Yes, you did. Thank you.
Okay, thanks.
More questions from the audience? I have a question, Mario. Can you please explain us how in which consists this convolutional neural network and how do you implement it for selecting the events?
Yeah, well, as I was saying, basically this is a machine learning process, which allow, well, what we do is we know that a characteristic way of a specific event. So for instance, these three events, we know the characteristic of this event. So there is this image. We literally have a lot of images of this kind coming from the detectors. So what we do is through this convolutional neural network, we say to the machine, okay, look, this kind of process, this kind of picture correspond to muon neutrino. This other picture correspond to electron neutrino and the other one. And then this is what they usually call the training processes. I give to the computer, to the machine, the images corresponding to some events which I know, and later on the machine gradually learn how to identify each process and classify. Sorry, I am not an expert either on that aspect, but they eventually would learn to classify properly each image to a specific process in the detector. And then the convolutional neural network eventually, and this is something appearing in the spectra as well, this is, the CNN here, the CNN corresponds to the, let's say, the index we give to each image, also each event, telling us how certain we are that that event corresponds to a neutrino, electron neutrino, or to a muon neutrino or neutral current event. In this case, for instance, well, this number is going from 0 to 1. And if it is a 1, it means that it is completely sure, we are definitely certain that it is an electron neutrino, for instance. And if it is lower, then the certainty is lower. And then we cut to some point. For instance, we select all events which are CNN, sorry, a value of the order of 0.7, let's say, and we count those events with as if they were electron neutrinos or muon neutrinos or whatever. So, but the whole process is, sorry, the whole process is a machine learning process, including some data which, or some information which is given to train the whole software, and then all the data coming from the detector to the machine to select it according to what it has learned. Basically, it's a pattern recognition technique. It is said that it's similar to what, for instance, Facebook does to classify photos, and whether you find a person, then it tags it with your name or the other, and basically it's the same situation here. I cannot hear you. I think you have your mic off. No, I don't hear you very well, actually. I don't hear you at all.
Sorry, Mario. I didn't realize that I wasn't that I muted. So there are more questions from the audience.
In the meanwhile, I'm sorry, I will move a little bit because I have to plug my computer, but I'm here.
If there are no more questions from the audience, we send Mario Acero for the very nice and complete talk.
Okay.
And we meet for the next seminar.
All right. Antonio, can you hear me?
I can hear you, Mario. Yes.
Oh, okay. I lost control of my computer, unfortunately. So, but well, thank you very much for the invitation. It was a pleasure to me to present this seminar. And well, thank you really, and all for your question as well.
Many thanks, Mario. Thanks a lot for the very nice seminar.
All right, thanks.
We look forward to see you at HEP conference.
Hopefully, yeah, me too.
Thank you. Bye.
Bye.
Bye-bye, thanks.
Bye.
Bye.
Bye.